Hello students, welcome to EPG Pathshala. I am Dr. Devrat Misra from Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the module Optical Properties Second from paper Electronic, Magnetic and Optical Properties of Materials. So students, let's see what we are going to learn in this module. Relation between amplitude, reflection and transmission coefficients, and we'll also learn about the relation between intensity, reflectance and transmittance. Fresnel's equation, amplitude, reflection and transmission coefficient. Although the ray picture with constant phase wavefront is useful in understanding refraction and reflection, to obtain the magnitude of the reflected and refractive waves and their relative phases, we need to consider the electric field in the light wave. The electric field in the wave must be perpendicular to the direction of propagation as shown in figure 1. We can resolve the field EI of the incident wave into two components, one in the plane of incidence, that is EI parallel, and the other perpendicular to the plane of incidence, EI perpendicular. The plane of incidence is defined as the plane containing the incident and the reflected rays, which in figure 1 corresponds to the plane of the paper. Similarly, for both the reflected and transmitted wave, we will have field components parallel and perpendicular to the plane of incidence, that is ER parallel, ER perpendicular, ET parallel and ET perpendicular. As apparent from figure 1, the incident, transmitted and reflected waves all have a wave vector component along the z direction, that is, they have an effective velocity along z. The fields EI perpendicular, ER parallel and ET perpendicular are all perpendicular to the z direction. These waves are called transverse electric field or TE waves. On the other hand, waves with EI parallel and ER parallel and ET parallel only have their magnetic field components perpendicular to the z direction, and these are called transverse magnetic field, that is TM waves. We will describe the incident, reflected and refracted waves by the exponential representation of a travelling wave, that is EI is equal to EI0 exponential over j of omega t minus ki dot r. ER is equal to ER0 exponential of j of omega t minus kr dot r, and ET is equal to ET0 exponential j of omega t minus kt dot r, where r is the position vector. The wave vector ki, kr and kt describe respectively the directions of the incident, reflected and transmitted waves, and EI0, ER0 and ET0 are the respective amplitudes. Any phase changes such as phi r and phi t in the reflected and transmitted waves with respect to the phase of the incident wave are incorporated into the complex amplitudes ER0 and ET0. Our objective is to find ER0 and ET0 with respect to EI0. We should note that similar equations can be stated for the magnetic field components in the incident, reflected and transmitted waves, but these will be perpendicular to the corresponding electric fields. The electric and magnetic fields anywhere on the wave must be perpendicular to each other as a requirement of electromagnetic wave theory. This means that with E parallel in the electromagnetic wave, we have a magnetic field E perpendicular associated with it such that B perpendicular is n by C E parallel. Similarly, E perpendicular will have a magnetic field B parallel associated with it such that B parallel is equal to n by C into E perpendicular. There are two useful fundamental rules in electromagnetism that govern the behavior of the electric and magnetic fields at a boundary between two dielectric media, which we can arbitrarily label as 1 and 2. These rules are called boundary conditions. The first states that the electric field that is tangential to the boundary surface E tangential must be continuous across the boundary from medium 1 to 2, that is at the boundary y is equal to 0 as shown in figure. The figure 1 represents light wave traveling in a denser medium strikes a less dense medium. The plane of incidence is the plane of the paper and is perpendicular to the flat interface between the two media. The electric field is normal to the direction of propagation. It can be resolved into perpendicular and parallel components. So E tangential 1 is equal to E tangential 2. The second rule is that the tangential component of the magnetic field B tangential to the boundary must be likewise continuous from medium 1 to 2, provided that the two media are non-magnetic. So relative permittivity mu r is equal to 1, and B tangential of 1 first medium is equal to the B tangential of the second medium. Using these boundary conditions for fields at y is equal to 0 and the relationship between the electric and magnetic fields, we can find the reflected and transmitted waves in terms of the incident wave. The boundary conditions can only be satisfied if the reflection and incident angles are equal, that is theta r is equal to theta I, and the angles for the transmitted and incident waves obey Snell's law, that is n1 sin theta I is equal to n2 sin theta r. Applying the boundary conditions to the electromagnetic wave going from medium 1 to 2, the amplitudes of the reflected and transmitted waves can be readily obtained in terms of n1, n2 and the incidence angle theta I alone. These relationships are called Fresnel's equation. If we define n is equal to n2 by n1 as the relative refractive index of medium 2 to that of 1, then the reflection and transmission coefficients for E perpendicular R perpendicular is equal to ER0 perpendicular divided by EI0 perpendicular, which is equal to cos theta I minus whole square of n square minus sin square theta I whole divided by cos theta I plus whole square of n square minus sin square theta I, and T perpendicular is equal to 2 cos theta I by cos theta I plus n square minus sin square theta I whole square. There are corresponding coefficients for the E parallel fields with corresponding reflection and transmission coefficient R perpendicular and T perpendicular. R parallel is equal to ER0 parallel divided by EI0 parallel, which is equal to square root of n square minus sin square theta I minus n square cos theta I whole divided by square root of n square minus sin square theta I plus n square cos theta I, and T parallel is equal to T0 parallel by EI0 parallel, which is equal to 2n cos theta I divided by n square minus sin square theta I whole square root plus n square cos theta I. Further, the reflection and transmission coefficients are related by R parallel plus n T parallel is equal to 1 and R perpendicular plus 1 is equal to T perpendicular. The significance of these equations is that they allow the amplitudes and phases of the reflected and transmitted waves to be determined from the coefficients R perpendicular, R parallel, T parallel and T perpendicular. For convenience, we take EI0 to be a real number so that the phase angles of R perpendicular and T perpendicular correspond to the phase changes measured with respect to the incident wave. For example, if R perpendicular is a complex quantity, then we can write this as R perpendicular is equal to modulus of R perpendicular into exponential of minus j phi perpendicular, where modulus of R perpendicular and phi perpendicular represents the relative amplitude and phase of the reflected wave with respect to the incident wave for the field perpendicular to the plane of incidence. Of course, when modulus of R perpendicular is a real quantity, then a positive number represents no phase shift and a negative number is a phase shift of 180 degree or pi. As with all waves, a negative sign corresponds to a 180-degree phase shift. Complex coefficients can only be obtained from Fresnel's equation if the terms under the square roots become negative, and this can only happen when n is less than 1 or and also when theta is greater than theta c, the critical angle. Thus, phase changes other than 0 or 180 degree occur only when there is total internal reflection. Figure 2a shows how the magnitudes of the reflection coefficient modulus of r perpendicular and r modulus of r parallel vary with the incidence angle theta I for a light wave traveling from a more dense medium n1 is equal to 1.44 to a less dense medium n2 is equal to 1.00 as predicted by Fresnel's equation. Figure 2b shows the changes in the phase of the reflected wave phi perpendicular and phi parallel with theta I, the critical angle theta c, as determined from sin theta c is equal to n2 by n1, in this case is 44 degree. It is clear that for incidence close to normal small theta I, there is no phase change in the reflected wave. For example, putting normal incidence, that is theta is equal to 0, into Fresnel's equation, we find r parallel is equal to r perpendicular, which is equal to n1 minus n2 by n1 plus n2. Figure shows the magnitude of reflection coefficient r parallel and r perpendicular versus the angle of incidence theta I for n1 is equal to 1.44 and n2 is equal to 1.0. The critical angle is 44 degree, and B shows the corresponding phase changes phi parallel and phi perpendicular versus incident angle. This is a positive quantity for n1 is greater than n2, which means that the reflected wave suffers no phase change. This is confirmed by phi perpendicular and phi parallel in figure 2b. As the incidence angle increases, eventually r parallel becomes 0 at an angle of about 35 degree. We can find this special incidence angle labeled as theta p by solving the Fresnel's equation, equation 2 for r parallel is equal to 0. The field in the reflected wave is then always perpendicular to the plane of incidence and hence well defined. This special angle is called the polarization angle or Brewster's angle, and from equation 8 is given by tan theta p is equal to n2 by n1. The reflected wave is then said to be linearly polarized because it contains electric field oscillations that are contained within a well-defined plane which is perpendicular to the plane of incidence and also to the direction of propagation. Electric field oscillations in unpolarized light, on the other hand, can be in any one of an infinite number of directions that are perpendicular to the direction of propagation. In linearly polarized light, however, the field oscillations are contained within a well-defined plane. Light emitted from many light sources such as a tungsten light bulb or an LED diode is unpolarized, and the field is randomly oriented in a direction that is perpendicular to the direction of propagation. For incidence angles greater than theta p but smaller than theta c, Fresnel's equation, that is equation 8, gives a negative number for r parallel, which indicates a phase shift of 180 degree as shown in phi parallel in figure 2b. The magnitudes of both r parallel and r perpendicular increase with theta I as apparent in figure 2a. At the critical angle and beyond past 44 degree, that is when theta I is greater than theta c, the magnitudes of both r parallel and r perpendicular go to unity. So the reflected wave has the same amplitude as the incident wave. The incident wave has suffered total internal reflection. When theta is greater than theta c in the presence of total internal reflection, the equations 6 to 9 are complex quantities because then sin theta is greater than n and the terms under the square roots become negative. The reflection coefficients become complex quantities of the type r perpendicular is equal to 1 exponential of minus j phi perpendicular and r parallel is equal to 1. exponential of minus j phi parallel with the phase angles phi perpendicular and phi parallel being other than 0 or 180 degree. The reflected wave therefore suffers phase changes phi perpendicular and phi parallel in the components E perpendicular and E parallel. These phase changes depend on the incidence angle as apparent in figure 2b and on N1 and N2. The reflection coefficients in figure 3 consider the case in which N1 is greater than N2. When light approaches the boundary from the higher index side, that is N1 is greater than N2, the reflection is said to be internal reflection, and at normal incidence there is no phase change. On the other hand, if light approaches the boundary from the lower index side, that is N1 is less than N2, then it is called external reflection. Thus, in external reflection, light becomes reflected by the surface of an optically denser, higher refractive index medium. There is an important difference between the two. Figure 3 shows how the reflection coefficients R perpendicular and R parallel depend on the incidence angle theta I. For external reflection, N1 is equal to 1 and N2 is equal to 1.44. At normal incidence, both coefficients are negative, which means that in external reflection at normal incidence, there is a phase shift of 180 degree. Further, R parallel goes through 0 at the Brewster's angle theta p given by equation 12. At this angle of incidence, the reflected wave is polarized in the E perpendicular component only. Transmitted light in both internal reflection, that is when theta I is less than theta c, and external reflection does not experience a phase shift. Figure 3 shows the reflection coefficients R parallel and R perpendicular versus angle of incidence theta I for N1 is equal to 1 and N2 is equal to 1.44. And figure 4 shows when theta is greater than theta c for a plane wave that is reflected, there is an evanescent wave at the boundary propagating along z. What happens to the transmitted wave when theta I is greater than theta c? According to the boundary conditions, there must still be an electric field in medium 2. Otherwise, the boundary conditions cannot be satisfied. When theta I is greater than theta c, the field in medium 2 is a wave that travels near the surface of the boundary along the z direction as depicted in figure 4. The wave is called an evanescent wave and advances along z with its field decreasing as we move into medium 2, that is Et perpendicular, which is a function of yzt, is proportional to e to the power minus alpha 2 y exponential of j omega t minus kiz into z, where kiz is equal to ki sin theta I. The wave vector of the incident wave is along the z-axis, and alpha 2 is an attenuation coefficient for the electric field penetrating into medium 2, where alpha 2 is equal to 2 pi n2 by lambda into whole of n1 minus n2 square into sin square theta I minus 1, where lambda is the free space wavelength. According to equation 13, the evanescent wave travels along z and has an amplitude that decays exponentially as we move from the boundary into the medium 2 along y as shown in figure 1b. The field of the evanescent wave is e to the power minus 1 in medium 2, where y is equal to 1 by alpha 2, which is called the penetration depth. It is not difficult to show that the evanescent wave is correctly predicted by Snell's law when theta I is greater than theta c. The evanescent wave propagates along the boundary, that is along z direction, with the same speed as the z component velocity of the incident and reflected waves. In past, we had assumed that the incident and reflected waves were plane waves, that is, of infinite extent. If we were to extend the plane wave fronts on the reflected waves, these would cut the boundary as shown in figure 4. The evanescent wave traveling along z can be thought of as arising from these plane wave fronts at the boundary as in figure 4. The evanescent wave is important in light propagation in optical waveguides such as in optical fibers. If the incident wave is a narrow beam of light, for example from a laser pointer, then the reflected beam would have the same cross section. There would still be an evanescent wave at the boundary, but it would exist only within the cross-sectional area of the reflected beam at the boundary. Intensity, reflectance and transmittance. It is frequently necessary to calculate the intensity or irradiance of the reflected and transmitted waves when light traveling in a medium of index n1 is incident at a boundary where the refractive index changes to n2. In some cases, we are simply interested in normal incidence where theta is equal to 0 degree. For example, in laser diode, light is reflected from the ends of an optical cavity where there is a change in the refractive index. Reflectance R measures the intensity of the reflected light with respect to that of the incident light and can be defined separately for electric field components parallel and perpendicular to the plane of incidence. The reflectance R perpendicular and R parallel are defined by R perpendicular is equal to ER0 perpendicular square, the modulus of EI0 perpendicular square, which is equal to R perpendicular square into capital R parallel is equal to ER0 parallel square divided by EI0 parallel square. From equation 9.37 to 9.40 with normal incidence, these are simply given by R is equal to R perpendicular is equal to R parallel is equal to N1 minus N2 by N1 plus N2 whole square. Since a glass medium has a refractive index of around 1.5, this means that typically 4% of the incident radiation on air glass surface will be reflected back. Transmittance T relates the intensity of the transmitted wave to that of the incident wave in a similar fashion to the reflectance. We must, however, consider that the transmitted wave is in a different medium, and further, its direction with respect to the boundary is also different by virtue of refraction. For normal incidence, the incident and transmitted beams are normal and the transmittances are defined and given by T is equal to T perpendicular is equal to T parallel is equal to 4 N1 N2 divided by N1 plus N2 whole square. Further, the fraction of light reflected and fraction transmitted must add to unity. Thus, R plus T is equal to 1. So, students, let us summarize what we have learnt in this module. So, we learnt the relation between amplitude reflection and transmission coefficient, and also the relation between intensity, reflectance and transmittance. Thank you.